In the previous video, we talked about the power of the TLC plate and the stationary phase that's on the TLC plate. So in this video, we're going to turn our discussion to the actual solvents that we use in the TLC preparation and developing. So the TLC solvents are going to play a role as well. So TLC plates have our stationary phase. And we said that polarity plays a really big role in how things begin to separate on the TLC plate. Well, that's only one half the picture, right? Because the other half of the picture is the solvent that we're choosing for the TLC analysis. Now, very often, what you see is a reverse combo. When I say that, I'm saying that if you have a polar stationary phase, then you will typically have a nonpolar mobile phase that pairs with that. Very rarely will you actually get a full-blown polar mobile phase as well as a full-blown polar stationary phase. It just doesn't do anything for your separation that much. So it's better to have both worlds. It's better to have your cake and eat it too. And that's why we have a polar and a non-polar combination almost every single time. Okay? Now, if the stationary phase is nonpolar, then it's probably better to have a polar mobile phase that pairs with that. Okay, so it's going to be basically up to you. What kind of stationary phase do you need? That's typically where we start. And then when you pick out that stationary phase, you'll then pick out a complement mobile phase to go along with it. Now, that's not to say that we can't put polar mobile phases into the picture, because we can. Sometimes it does work. But what I'm saying here is that generally, you either have nonpolar, polar, stationary phases and mobile phases, or the reverse. You never really have both at the same time. Now, with that said, let's talk about some of these mobile phases. Some of the mobile phases that can be used in TLC. You can play around with the polarity all that you want. We can use very simple alkanes in our development. Okay, these alkanes would be things like hexanes, 6-carbon chain, right? Petroleum ether. That is a non-polar, organic natured solvent. Very common in a laboratory. Well, we can increase the polarity a little bit, and we can throw in ring structures maybe that has some delocalization. So those would be things like toluene, right? Toluene would be a very good choice. It's still non-polar. It's still mainly carbon and hydrogen, but delocalization is there. Some electrons can move around. There's some double bonds involved. And because there's double bonds present, then the polarity changes up a little bit. We can then go to halogenated, and I'm going to write that as a X because that's how organic chemists write halogens. They use an X there. Halogenated hydrocarbons. All right, so halogenated hydrocarbons basically mean things with bromine or chlorine or iodine on them. So this would be something like methylene chloride, and methylene chloride again is abbreviated MECl2, methylene chloride. This is also known as dichloromethane, and that has its own abbreviation as DCM. We're increasing polarity a little bit there because we've increased a halogen, and that increases the electrons that are present. Each halogen has 6 sets, right? Chlorine's got, or 3 sets. Chlorine has 3 sets of chlorines around it, or electrons around it when it's attached to a compound. So does bromine, so does iodine. You learned that in organic chemistry, hopefully. Well, we can increase the polarity even more from that, and we can bring in typically ethers. Now, petroleum ether is a little different. That is an ether, but the problem is that the carbons outweigh that ether. So when we talk about ethyl here, we're talking about diethyl ether, which is CH3, CH2. There's the first ethyl group, an oxygen, and then the other ethyl group of CH2 and CH3. That is organic. There's some carbons, there's some hydrogens, but we've got these pairs of electrons on the oxygen on the center, right here. And that creates some polarity that's associated with the solvent. Now, the number of carbons are not as great as PET ether would be, which is why this is more polar. Finally, we can kind of stay in the world of organic, and we can choose things like acetone. Acetone is going to be a ketone because of the ONE ending, and those ketones are going to be very similar to an ether. Those ketones basically have a carbon double bond O. So not only do you get some double bonds here, but you actually get some more electrons as well wherever those get associated with themselves. If you're looking at acetone, that's basically 2 carbons, so we're not talking about a lot of carbons here at all. So we're limiting the carbons and we're increasing the double bonds and the electron pairs in a molecule. So it makes it become more polar. Finally, not finally, but almost finally, are the alcohols. Alcohols are very common as far as polarity goes. The issue here, though, is most of the alcohols, if you want them to be polar, would be less than 4. So here I'm going to put the more polar ones have carbon numbers that are less than 4. So this would be butanol, propanol, ethanol, and methanol. Those are very, very polar. However, if you have carbon numbers that are greater than 5, this is another one of those things that you should have learned in organic. These things become non-polar. They're more organic in nature now. So I'm not saying that the polarity goes away. It's still present. But these alcohols are not as polar as the first 4 carbons. The polarity changes quite a bit when you reach the pentane or the pentanol mark and go pentanol, hexanol, heptanol, octanol, and so on. And then finally, down here at the very bottom, if you really want to do a superpolar acid and you want to increase the polarity here, you would use something like acetic acid. Some of these basically C double bond O, OH molecules. Carboxylic acids would also work. Those are very polar. We see some delocalization that can be present. We see some free pairs of electrons that can be here on this oxygen. It can also be here on this oxygen. Those things can float around in the entire molecule. So we increase our polarity because of that. So there's kind of a ranking of the mobile phases. And I'm not saying that you have to pick just one, because very often in the world of TLC, you can mix any or all of these together. And you can play with the polarity that will make your solvents suitable to separate the components that are in your sample that's been delivered to the laboratory. So the directions will tell you basically what to do. If you're following a laboratory method, they're basically going to tell you these are the solvents that you're going to pick. This is what's required to separate these things in a laboratory. But now you kind of understand why these solvents are picked the way that they are. They're playing around with the polarity of the solvent. Sometimes we need to increase the polarity of those mobile phases so that way we can get very clean dots and circles on our TLC plate. But there's kind of the order that you would see it. So silicous polar, you would probably pick a non-polar mobile phase, which means that you're probably going to be playing around with your toluenes and your hydrocarbons and your ethers a little bit more. But don't be surprised. if the directions tell you to throw in a little bit of acid or throw in a little bit of alcohol, because that's helping increase your separation for these polar compounds. So again, it's two sides of the same story. We've talked about the stationary phase, and now we've talked about the mobile phase. Both of them are as important. Both of them need attention, and you need to make sure that you carefully choose both of them in a laboratory to separate your compounds.